In this lecture on dry etching, we are going to look at the mechanism. So what is the mechanism that determines the combination of gases that we use will remove material? Because we also saw plasma can also be used to deposit material. So we have to find the right condition for the precursor gases that we use to remove material instead of deposition, or in some cases no reaction at all. Right? The worst thing is depositing instead of removing, but then not removing anything is also something undesirable. So let's look at how these mechanisms are studied and what you need in order to make these radicals etch the material. So in order to create any etching, right, we need to first create reactive species, right, in the system. When I say in the system, meaning the plasma and the wafer and the chamber, right. So we need to have reactive species, and these reactive species should produce volatile product. So they should react with the substrate and create volatile product, which is very important. So if you create non-volatile product, it becomes deposition. So here we need to create volatile product. And not only just create volatile product, we should be able to remove the product outside the system. So these are all the three primary requirements, right. So you need to have reactive species, and these reactive species should be able to create volatile products when it reacts with the substrate, and then these volatile products should be removed out of the system. So this is what a simple system to study the plasma etching. So how the etching happens, what is the contribution of reactive neutrals and the ions and so on. So what people have done is they have taken a thin sheet of material that you are interested in, and there is a beam of iron that is shot onto the surface, and then also a beam of reactive neutrals is also shot. There are various neutrals that can be used for etching, and then the etch byproduct is sent to a mass spectrometer to study what this product contain, right, what is the chemical nature of this, and the etch rate is monitored by looking at the thickness, right, through a quartz crystal. So you are looking at what is the thickness by measuring the quartz crystal frequency and so on. Okay, so the etch rate is measured as well. So all these things are done simultaneously in order to understand the mechanism. So let's look at the contribution of ions, right. We have been talking about the importance of iron, looking at iron flux and iron energy and so on. So this is a classic experiment that was done to really explain the importance of iron, right. So in this case, this is a silicon etch, right, and xenon fluoride is the gas used. It is known xenon fluoride will etch silicon, but just when you flow xenon fluoride on silicon, the etch rate is almost nothing, right. So there is no etch observed, right, no considerable etch observed when you pass through xenon fluoride, right. But then we beam this argon, right. So the argon ions are now shot. So initially we had xenon fluoride, right, but now we are going to shoot argon ions, right. So these are all ions. So the moment we switch on argon ion, we see increase in the etch rate, right. The etch rate shoots up and then it plateaus. Okay. So the etch rate increases, right, compared to here. The etch rate increases in the presence of iron. Okay. So now we want to know whether iron alone can etch, right. So then you take out xenon fluoride from the system, right. When you take out xenon fluoride now from the system, you look at the etch rate, and again the etch rate comes down. So there is no etch with argon ion only. So the conclusion of this experiment was you need both the gas, the etching gas, and also the ion to etch. Ion alone is not etching, they are inert, and then xenon fluoride alone was unable to etch, but you need both of these to etch the material. And this is again multiple confirmation on the etching, but in this case some interesting experiment was done with halide and argon to show not only etching, you can also have deposition and so on. So on the left side this experiment was conducted on aluminium. So you take aluminium and you expose aluminium to argon ion now. So right, argon ion only, and then you see an etch rate of about 15 angstrom per minute. The moment you pass fluorine, the etch rate actually goes down, right? So the etch rate goes down, and then you are reducing the etch rate. So though fluorine is is known to be a radical, but it is reducing the etch rate, right? But on the other hand, you take silicon and then you start with argon, right? So argon gives you a very abysmally low etch rate of 2 or 3 angstrom per minute, but then I bring in chlorine now. When you bring in chlorine, the etch rate increases. So the reason for that is creation of non-volatile products and creation of volatile products. So in case of silicon, you generate SiCl4, which is a gas, right? So in aluminum case, you create aluminum fluoride, which is a non-volatile substance that creates a coating, right? This coating is the one that is preventing your argon atoms to etch. Okay, so the ions that are present there is not only the main component, also depends on what is the gas that you put in, right? And ions we have looked at, and then now we also know the neutral gas contribution. But what is the contribution of electrons here? Because we said electrons are the most important constituents in plasma, and this experiment was done just to validate the contribution of electrons here, right? So so first started with xenon fluoride, right? And when you put only xenon fluoride, there was not much or no etching at all, right? So there was only xenon fluoride, but then you start illuminating or exposing the material to electron beam now, right? But now when you expose it, you start seeing some etching, right? So this etching also indicates that electron can participate or enable this etching, but then the problem here is the amount of material that is removed is very, very small. Okay, so you're talking about 200 angstrom per minute for 1.5 kV of energy, right? That is required to remove oxide. So electrons are not directly involved in the process of etching, right? What they are trying to do is participate in this and then create ions, right? So that is what they are good at, right? So they neutralize the charge created by the positive ions in the RAE system, right? So they are not actually participating in actively removing the material. So let's look at how do we achieve directionality by using ions, right? So ions are important, we all know. So and particularly positive ions are highly directional, because if you remember we had the blocking capacitor along with your RF, right, which is grounded, and this VDC, right? So VDC was negative, right? So when you have a negative VDC, you will attract positive ions, right? So you will have positive ions attracted towards your substrate. And the neutral species are random because they don't respond to any voltage that you apply. But the important thing is the neutral species are the one that are involved in reaction. Okay, you have this fluorine, right, the chlorine, they are the neutral species that are involved in the reaction, but you cannot control their movement. So their movement cannot be controlled because of neutral nature, but the ion positive ions could be controlled by applying this field, right? And that is the main property here. Wherever you have ions coming in, if it finds the radical, then the energy is transferred, right? And this energy transfer allows fluorine to react with silicon, let's say. Okay, so there is a additional energy that is required to enable this reaction, and that additional energy is coming from the positive ions. And how do you achieve directionality? Is by only creating those access point where you encounter the fluorine atom with this positive ions only on this surface, not on the sidewall, because fluorine is also present on the sidewall, but you don't want positive ions to go onto the sidewall, which will enable this reaction. Okay, so you want all the positive ions to be very directional. And let's look at the importance of ions in terms of chemistry as well, right? So let's take aluminium, right? So aluminium as an example, and then CCl4 is the gas, right, that we are going to expose, and it will generate a chlorine radical or CClX, let's say, right? So this is what it is going to generate. But then when you look at the experiment, right, when you don't have any ion bombardment, when you expose it with chlorine, people observed an isotropic etching, right? So chlorine etches aluminium, but in an isotropic way, in the absence of ion. But when you look at CClX, right, so CCl was not etching at all. So no etching whatsoever when there is an absence of ion. But then now when you initiate ion bombardment, so now we are going to put some ion. This ion can be, let's say, argon, right? But chlorine has no change in the profile at all, because the reason for that is it's an isotropic etch. Anyway, the radicals are etching both vertical and horizontal at the same rate. But CCl was not etching initially, but when you expose it with the iron, now you start etching the material very directionally. That is the most important thing. It not only etching, but it is etching in a directional fashion. That directionality comes from the directionality of ion that we are shooting. Okay, so if you shoot the ions with a different angle, you will also see angled edge, but in this case we are shooting in a directional fashion, and this actually confirmed that though the radical was unable to etch the material, but if I add an ion to this, then this will etch the material that initially it was unable to etch. And this also confirms that your ions are very important. So another way of another thing that was observed in this experiment was creation of a thin non-volatile film, right? So normally we generate non-volatile products when you are etching, but you will also have reaction paths where you will end up with non-volatile films. So in this case, whatever product that was generated, you will take it out, and the non-volatile products, they came and deposited onto this sidewall, right? And you start accumulating this, and this actually protected the sidewall. And by doing this, you create anisotropy. You only expose your ions to this and radicals to this. Okay. So the deposition chemistry, it depends on the etch rate, because as we saw, you also start depositing, right? In the earlier case, that was the conclusion. So you generate volatile products. You also generate non-volatile products. So you should make sure that your etch rates are higher than deposition rates. So this is very important. So what is the appropriate ratio of etching and the condensation, or deposition on this the wafer, right? So by operating beyond the deposition point, you can create anisotropic profile. Okay, and you can also do cycling, right? This we will see later. You can do both etching and deposition in the same process. You can etch by controlling the ratio, and then you can move into deposition, and then you can come to etch and then move to deposition, which is something that is used in deep silicon etch, which is called Bosch process. So in that process we use etching and deposition in a sequential fashion. This is actually a characterization of how the protective layer forms, and we use that protective layer to create anisotropy. The cartoon on the left gives you a comprehensive picture of what goes on, right, between the plasma and the substrate. So the feed gas and the chamber wall condition and everything creates the plasma, and from the plasma you get all the radicals with the ions, right, to react with the substrate, right? And these substrates would create, the reaction would create byproducts. So either the byproducts to the plasma or byproducts to the side wall. But when the byproduct sits on the side wall, it's going to protect my material here, and then I can only get access to the material at the bottom for etching. And the resist, it's also is participating in this whole reaction, right? The mask, the photo mask that we use, if the material can be etched with the plasma that we generate, ideally you don't want any reaction, but we never get infinite selectivity, right? So the material selectivity, let's say 1 to 100, right? So 1 nanometer of mask material is removed, right, while 100 nanometer of silicon is removed, let's say, right? But it's 1 nanometer is removed nonetheless. So that removed material also goes into the plasma, and also it can feed for the sidewall coating as well. So the ACM picture on the right side, right, this is silicon with photoresist. So what you see here is the photoresist area, right, and what you see here is this strange coating that you see, right? And when you don't remove it, you can see here the side walls are pretty good, right, 90 degree or so. But then when you clean it, right, so when you clean the material, right, the photoresist, and strip the material, you will see that it's not 90 anymore. There is an angle. So the angle is coming from the passivation layer, the protective layer on the sidewalls, and the thickness of this protective sidewall layer varies from top to bottom. The reason for that is the top portion is exposed longer. Okay, so this portion was the first portion to be etched, and then as you go deeper and deeper, whatever you generate is deposited on the top, right? So that is the reason why you have a a sloped sidewall, because the thickness of the passivation layer is thicker at the top. So it is not just the chemistry and the ions that are dictating the etch. It's also the surface temperature. The surface temperature of the wafer also determines the etch rate and directionality as well. So in this experiment, what was observed, when you reduce the temperature, the silicon etch rate increases, right? So there was an increase in silicon etch rate, while silicon dioxide and photoresist etch rate was going down when you reduce the temperature. So one can use this as a way to improve selectivity between photoresist and the material that you are etching, or also increase your etch rate, right, at lower temperatures. So it's not just the etch rate, it is also the directionality. So what is directionality? Directionality is the difference between the vertical and the horizontal etch rate. So we will call it highly directional or anisotropic when B is almost 0, right? So you want it to be very low. So how to achieve that is the question here. In this case, we are trying to reduce the temperature and see the effect of this directionality. So as you can see, when you reduce the temperature, your directionality gets better. The reason for this is when you take a surface and then when your radicals land on the wafer, they will always diffuse, right? So there is a diffusion length associated with this radical, and this strongly depends on the temperature. So when you reduce the temperature, your diffusion length is reduced because you are not supplying energy to this radicals, right? So because of that reduction in the energy, you reduce the migration of these radicals, and this is how you achieve a reduction in the lateral edge and improve your vertical edge, and that results in very high directionality. So with this we are able to understand the etch mechanism. Okay, so the ion flux, the ion energy, and the presence of ions, right? Even if you have the etching radicals, you need ions. Without the ions, you won't have any reaction. So we saw that clearly in the mechanism, and also we saw how do you control the anisotropy. When you don't have any sidewall coating, you will create isotropic edge. By creating this sidewall coating, you will create anisotropy. And also you can use the directional ions in order to create anisotropy. If the ions are not directional, you will create isotropic edge as well. So and finally we also saw it's not just the chemistry and the ion energies, the temperature also plays an important role. Based on your temperature, your etch rates could change. Also your directionality will also have an effect.